So we have a number, and we want to write it to the EEPROM, and it's a 2-byte number. So it's an integer, it's got 2 bytes, and in this case we use the number 259. So 259 in binary is shown there at the top, sequence of zeros and ones. And notice it has 3 ones in it, okay? It's got 16 bit positions total, but in binary, 3 of those bit positions are ones, the rest is zeros. The least significant 2 bits are ones, and the bit in the 8th position is a 1. And the rest of them are zeros. So that's 259. And we want to put that into EEPROM. So first, we want to just focus on the least significant byte. Then we want to focus on the most significant byte. So the least significant byte are the least significant 8 bits, and they include 2 of those ones. Okay? The low 2, the least significant ones are in there. Then the most significant byte has that other 1 in it. So we want to focus on the least significant byte first. So how do we do that? What we do is we create a mask. Now the mask you can see is valued 255. That's its decimal representation. But in binary you see it right there underneath the 255. It's high, basically it looks like its high bits, high 8 bits are all zeros, and its low 8 bits, which are highlighted in red, are all ones. So what this is trying to tell us is, in our mask, is that the bits that we are interested in our original number, 259, are the low bits, the least significant 8 bits. Those are the ones that the mask has assigned to 1. So those are going to be the bits, those least significant 8 bits inside 259, those are the ones that we're interested in right now. So now what do? We take the mask and AND it, perform a bitwise AND with the number 259. So we take 259 ANDed with 255, which it's easier to see what that does if we look at the binary representations. So we do a bitwise AND. Now bitwise AND, so an AND operation is basically a logical operation. It takes zeros and ones, or highs and lows. And an AND operation only outputs a 1 if both the inputs are a 1. So if you AND 0 and 0, that's a 0. 0 and 1 is a 0. 1 and 0 is a 0. 1 and 1 is a 1. Right? So that's an AND. So a bitwise AND, what that does is it performs ANDs, like I just said, on every pair of bits in the 2 numbers. So if we look at those 2 numbers, 259 and 255, look at their bit representations, they're 16-bit numbers. So what actually happens when you do a bitwise AND is it performs 16 different AND operations. So it takes the least significant bits, the bits in the 0th position, ANDs those. And then it gets the 0th position of the result, which in our case, if you look at the mask, its 0th bit is a 1, and the 0th bit, the least significant bit of 259, is also a 1. You AND 1 and 1, you get a 1. So the result is a 1, right? In the bottom row, that result you see is a 1 in that least significant bit. You can say the same thing for bit position 1. Yeah, there's a 1 in 259 in that bit position, and there's a 1 in the mask in that position. So you get a 1 in the result, in the position number 1. Now when you go to position number 2, you get a 0 in 259, right? So whenever you AND something with a 0, you get a 0. So when in that bit position in the result, you see a 0, and so on. So the key here is that when you AND something, when you take, in this case, we're taking the least significant 8 bits of 259 and ANDing them with ones, because the mask has all ones. When you take a number, bitwise AND it with ones, you get that same number back. So you'll notice in the result at the bottom, the least significant 8 bits are exactly the same as the least significant 8 bits of the number 259 that we're interested in. Now, the most significant bits of the mask are all zeros. So we're ANDing the most significant bits of 259 with the most significant bits of the mask. And anytime you AND a number with a 0, you get a 0. So you notice in the results, and the result at the bottom, the most significant 8 bits are all zeros, even though that wasn't the case in 259. 259 actually had a 1 in bit position number 8. But because you ANDed it with that 0 in the mask, it got zeroed out. So all the most significant 8 bits are all zeroed out in the result. And what this effectively does is allows us to focus on only the bits we want. So we put ones in the least significant 8 bits because those are the only bits that we're actually interested in right now. Because with our EEPROM, we're going to only write 1 byte at a time, one 8-bit chunk at a time. So this masking, you create the mask where you put ones in the bits and the mask bits that you're interested in, and then you perform a bitwise AND, and you see that ampersand right there. That's how you do bitwise AND. You perform a bitwise AND between the original number and the mask, and in the end you get a result where only the bits of interest that are highlighted by the mask as ones in the mask are the ones that you get in the result. So what we've done is if we look at the result, the least significant 8 bits are the ones that we want. And now we can take those least significant 8 bits and just write them to EEPROM. Now this example shows us how to get at the least significant 8 bits. We'll also want to look at the most significant 8 bits, right? So how do we do that? So there are a couple of ways to do it, but here's the way we're going to do it. We've got 259 again up at the top. This time we want to focus on those bits that we have in blue there, the most significant 8 bits, which are all zeros and then a 1. So first thing we're going to do is take that number, 259, and right shift it 8. Okay? So what does right shift mean? Right shift means just take the bits and shift them over 1. Okay? But we're going to shift it over 8. So we're going to take every bit in a position in 259, we're going to shift it over 8 positions. Now what this effectively does is that all those bits that are in the least significant 8 positions, they disappear, right? Because if you shift them over 8 bits, they're outside of the number. But what it does do is that the most significant 8 bits are now the least significant 8 bits. And you can see that where we have 259 at the top, we've got those highlighted blue. Now if you look at 259, right shift, greater than 8, right shifted 8, those same blue numbers have shifted over 8. So the most significant 8 are now the least significant 8. And the most significant bits are all zeros now, because when we did the right shift, when you're shifting into the end, you just shift zeros in. So you get zeros in the high bits. So now we've put the bits we're interested in the low 8 positions, and then we perform our same bitwise mask again. We bitwise AND with the mask. So we use that same mask we used in the last slide, which allows us to focus on the least significant 8 bits. And we use that same mask, and we get the result. So in the final result, you can see that what were originally the high 8 bits, the most significant 8 bits in 259, they've been shifted to the least significant 8 bits. And then by doing the masking, all we see in the final result are the least significant 8 bits, which are actually the most significant 8 bits of the original 259. And then all the high bits are zeroed out because of the masking operation. And then at that point, you can take that number and do an EEPROM write and write that byte into EEPROM, and you'll write the byte correctly. So here's a little program that shows that going on. We start off with an integer. We'll call this big data, some integer, 16 bits, that we're interested in. Okay, and we want to write this into the EEPROM into an address. Then you got a byte we'll call little data, which is what we're going to do is make little data 1 byte of big data. So we're going to take big data and first write 1 byte of it as little data and then another byte. So in the setup, we say little data equals big data and OXFF. So what does that mean? That is performing the bitwise AND with the mask. So OXFF is my mask. Now that notation is called hexadecimal notation, right? Hexadecimal notation, we didn't go over it, but hexadecimal means, so hexadecimal is base 16. And in base 16, your digits, you have 16 digits, 0 through 9, plus A, B, C, D, E, and F. Okay? So A is 10, B is 11, so on, and F is a 15. Okay? So notice as OX. OX means hexadecimal, and the actual value in hexadecimal is FF, and F is a 15, or which in binary is all ones, is 1111. So F is just 1111. So if I say FF, that's 1111, 1111. That is 8 ones in a row. That is exactly the same as the mask that we used before. All zeros and then just 8 ones. So OXFF is the same as the mask that we used on the last 2 slides. So this is just a shorthand. Now, people, you should be used to this shorthand a little bit because this hexadecimal shorthand is commonly used. It just makes numbers shorter, right? Rather than drawing 16 bits, I could just draw these Fs. OXFF is much shorter. So it's a common shorthand to be using when you're programming IoT devices. So, okay, so big data and OXFF, that does the bitwise masking, the bitwise AND with the mask OXFF. And so now little data is going to be the least significant byte. And then we can just write that, EEPROM write to location 0, little data. Then, now I say little data equals big data right shifted 8 and then masked. Right? So now little data is equal to what was the most significant byte inside big data. And then we write that. EEPROM write 1, comma little data. So note that we are writing the next byte into the next address, which we have to do, right? Because each address only takes 1 byte. So what we've done is we've done what's called little endian ordering, meaning we took the least significant byte and wrote it into the lowest address, 0. And we took the most significant byte and wrote it into the higher address, 1. That's called little endian ordering. We could have done it the other way. We could have said, well, I'm going to take the most significant byte and put that in address 0, and then the least significant byte, put that in address 1. That's called big endian ordering. And we can do it either way. And different hardware architectures, different machines do use different ordering. Some machines are little endian, some machines are big endian, and you need to be aware of that when you're working with a machine. But it's up to us. Since we're writing all the code, we can write it however we want to. But just a sort of side note there. This is little endian ordering. Thank you.